Okay, now the next proposition 6, or Theorem 3 of Euclid, Euclid's elements, I should say, rather, also about isosceles triangle, provides a complete description of isosceles and how to easily identify an isosceles triangle, and what exactly characterizes an isosceles triangle in terms of lengths and angles. And essentially what the theorem asserts is partly the reverse direction of the previous theorem, wherein we found that an isosceles triangle contains the base angles rather, of an isosceles triangle are equal. The next theorem takes that the other way around. We start with a triangle with two angles unknown. Two angles asserted to be equal, and we wish to show that that implies that the triangle must be an isosceles. Okay, so that means we have it forwards and backwards, and therefore the equal angles rule is an if and only if rule. It works both ways. I've actually written that down here in a summary. So proposition 6 of theorem 3, we've already established the following, that if these lines in any triangle happen to be equal, which is called an isosceles, then the base angles, in different colors here, happen to be equal. Proposition 6 states the opposite is true, and that is any triangle containing two angles the same must be an isosceles triangle. And I've put it in three other ways. As corollaries, or however you can say it. A triangle is an isosceles if and only if two of its angles are equal, or equivalently, a triangle is an isosceles if and only if two of its sides are equal, or mixing the two together, a triangle containing either two equal sides or two equal angles is an isosceles triangle. Okay, well, the first is by definition, the second is by theorem. Still, the symmetry is useful, and knowing this fact allows me, for instance, to construct an isosceles quite easily by simply constructing two equal angles. If I can find, if all I need to do is construct two equal angles, extend the lines from the vertices where those angles would meet with another line until I get a meeting point, and I've constructed an isosceles triangle. It also tells us that there is an isosceles triangle for every acute angle, right? To every acute angle, there is associated with it an isosceles triangle, because there is as long as two angles are the same in a triangle, then it must be an isosceles. And so we can choose any number for the same angles and build an isosceles out of it. I said acute angles. I don't think it would follow for any. You couldn't have two obtuse angles in a triangle, and that's something we would have to work out later. An obtuse angle is greater than a right angle. Two obtuse angles would be greater than two right angles, and if we could only establish that a triangle's interior angles add up to two right angles, then we could make the statement that I just made. As far as the proof goes, it's really quite simple. The way they've worded it is, I don't know if you can make this out, but there's a white underneath this here. There's a white line, and they use dots, but I don't have dots. So, can I grab? Oh, I got it. I repaired some of my grabbing so I can grab things with better accuracy. Okay, so this is a white, supposedly straight line, written in a way such that we can see it as two parts. Okay. Oh, I got it. Oh man, I'm getting lucky. Okay. Alright, and that'll be important in a minute. But here we're to assume that these sides are the same. Okay. No, sorry. That these angles are the same, and these sides may or may not be different. Alright? The theorem states that if two angles, this blob and this blob, are equal, then the sides, this and this, opposite them, are equal. Okay? Now, so that means if the white was over here, then it would be these sides, it would be equal. It's arbitrary in the sense of it doesn't matter where the two sides are placed, there's only one more position left, and so we always have two sides to compare. Now, for the sake of argument, one of the sides has been written as the sum of two parts, okay? And we're going to assume that the sides be not equal. If they're not equal, that means that one side would be greater in length than the other. That follows from the axiom that the whole is greater than the parts, right? No, it doesn't follow from that at all. We're just saying that they're not, if things are not equal, then either one is less or greater than the other, and we've chosen greater as the case that we're going to look at. Okay, you could equally run the argument around using the lesser. Now, given the fact from problem 3 that we have the ability to cut off from this the greater side, which is composed of parts, an amount equal to an amount that we would like to cut off we want to cut off from it the amount which is the other side, the blue side. Since this is greater than the blue side, then it must be that one of these lengths is blue, and we're allowed to cut off from any longer line, according to problem 3, an amount equal to some arbitrary given amount, and the given amount in this case is this side. So if we cut that off, then the white part will now be equal to the blue part, right? So essentially this has become the blue part. And from that blue part, underneath here, these are connected. Unfortunately, these lines don't have high priority for drawing. Okay, so what I've done here, what we've done is we've cut off the extra bit from our longer length side, and made a new triangle by drawing a yellow line from the end of this white bit to the vertex containing one of the angles. Alright? And I've just mentioned this is the only if part of the last statement. We have if, and now we're doing only if. The if meaning if it's an isosceles, then the angles are equal. Now we're doing it's an isosceles only if the angles are equal, essentially. Okay, so now we have this new triangle, and we have this other triangle where white is equal to blue. Alright? Now, by construction, that's what that construction should be at the end of this sentence. I ran out of room. But we've supposed, okay, that these two angles are equal. That's our hypothesis. In any triangle with two equal angles, right, we want to show that the sides have to be equal as well. So we've supposed that these angles are equal. And in common, these triangles have the baseline, which is red. Okay? Now we have two triangles which are equal. And by problem 4, and having equal angles, by problem 4, what we have is this angle, right, the same, red common to both. This has the same angle here and a common red. This one has a common side and the same angle, right? I just gotta get this right. If we don't have two sides equal, we have an equal side and an equal angle. But these are white equals to blue. Oh yes, okay. Blue and white are equal. And the two angles are equal. I should give them the same color. In this case, here we have two sides equal, white and blue, with a common base red, with the same angle assumed, right? And so therefore these angles are equal in every possible respect. However, it is clear that this triangle is only this line, and this length anyway, is only a part of this triangle, and so therefore what we have is a part being equal to the whole, and that is, I like to write it this way. So, and that is a total and absolute absurdity because that contradicts axiom, which axiom is that? The whole is equal to is greater than the part. Axiom 9 tells us that that is completely and utterly absurd, and so therefore we've run into a contradiction, and so therefore neither part is greater than the other part, and therefore the parts must be of the parts being spoken of are the angled sides, red is always the same. Neither of the angled sides is greater than the other, and so therefore they must be equal, and so we've established that if the angles are equal, then the two sides are equal, and it's an equilateral triangle, and so therefore now we have an equivalence between equal angles and equal sides. Equal angles imply equal sides, opposite sides. Okay? And that's pretty much the end of the story for the Isosceles triangle. And I don't think I'll add anything to it. I'm not going to go on to the next theorem because it's rather involved and that'll take a whole lesson. So that's it for this, just a quick one. The next theorem, I have to work this one out and figure out what this word means, counterminious. I can't find a definition for it. I don't have access to the internet, but perhaps by reading this through I can figure out what that word means. And just scanning forward, let's see what's coming up here. Here we're being given a procedure for bisecting a rectilinear angle. You see, I thought I could do it, but I can't. I couldn't because of the reasons I gave before. Bisecting an angle is crucial to the constructions to follow. Let's see what comes up. I'm just wondering how long before we find out that the interior angles add up to 180. I don't see it immediately. But it is coming out. Let's see. Here it looks like the beginnings of opposite angles are equal and stuff like that. Now look at a whole circle being placed around, and I bet you that by the end of this theorem, not that one maybe, anyway, I'm sure that soon enough we'll have established that as following from the axioms. Okay, So that's it. Very short one. See you next time.